data for the scale augmented distribution. I mean, it's a model, so not a distribution technically. And I'm gonna use one more notation, Pn. So which I'm gonna call the noise distribution. And this plays a key role in the noise contrastive estimation. And it has many aliases like reference distribution, contrasting distribution, proposal distributions, depending on the paper you will read in the literature. But yeah, these are all the same thing. Right, so here is the noise contrastive estimation objective function. So given a noise distribution Pn, and yeah, I'm gonna assume two things. So first, it is easy to draw a sample from this noise distribution. And also, it is easy to compute the density given X. Right? So suppose that you are given such a noise distribution Pn, then I'm gonna define the J and C theta as the expectation of the log of phi tilde over phi tilde plus Pn under the data generating distribution, plus expected value of log 1 minus of this, so that it becomes Pn over phi tilde plus Pn under the noise distribution. Okay. So this is the NC objective. And what we can prove is that if a given noise distribution Pn satisfies that the support of it subsumes the support of the data generating distribution, then the theta star, the parameter we are looking for, is the maximizer of the J and C theta. And I'm gonna prove why this is the case in the next slide. So you can believe me for now. And then as I told you before, given samples, what we can do is that we can approximate, we can approximate the ideal objective with given samples. So what I'm gonna do is I'm gonna replace this expectation with the Oracle distributions by the Monte Carlo approximation with samples. So given Xn drawn from the underlying data distribution, I'm gonna replace this expectation under PD by this, and I'm gonna plug in Xn to this. And then for the second expectation, I'm gonna draw n noise samples and plug in that into the expression so that I can get the unbiased estimator. So just one comment here is that you can use different sample size for sure to get a sample objective. But for simplicity, I'm going to assume that we are just drawing the same number of noise samples here. Okay, so this is what we are going to use in practice. So to estimate the parameter of the unnormalized distribution, given samples, we are going to compute this objective function. And as I mentioned before, typically we optimize it by, gradient-based methods, for example, stochastic gradient descent and so on. You can do that. And another comment is that I assume that it's easy to draw samples from the noise distribution, and it is easy to compute the density. So the two requirements are required because of the form of the objective function. So when we instantiate this this objective with samples, we approximate this by summation by drawing samples. So you have to, it should be easy to draw samples from it. And also you you should know how to evaluate the density, right? So those are required. Those are required. Any question? Okay.
Is there a intuitive meaning of this objective J?
Yeah, so I'm gonna give you the interpretation in the next slide.
Okay, thank you.
Right, so the typical standard interpretation of this noise contrastive estimation principle is based on the binary classification. So before I do that, let me just recap the problem of binary classification, and yeah, just to make it clear. Right, so in binary classification, we assumed two class densities, P0x and P1x. So in 1D case, you can consider a mixture of Gaussian for simplicity. So let's say this is the P0x and P1x. So what I meant by that is given label, so a data with label 0 follows this density, and a data point with label 1 follows this density. Okay, and I'm gonna take a uniform mixture for simplicity. So Px, the marginal distribution is gonna be 1/2 of P0x plus P1x. And the question in the binary classification is, given x, what is the probability of y being 1, the label being 1, or y being 0, right? And you can compute this by Bayes' rule. So probability of y being 1 given x under this mixture distribution is probability of y being 1, so the prior distribution times the px. So this is the class densities. This is what I meant by class densities, and we assume that that is going to be P1x and divided by this plus this, right? And since you assume the uniform weights, this is nothing but the ratio between P1x and P0x plus P1x, right? Then now it comes to the binary classification problem. So now let's suppose that we consider a probabilistic classifier eta theta x, which is supposed to approximate this probability of y being 1 given x equals x. The typical objective in binary classification is the binary cross entropy loss, which is defined as the given eta theta and given the sample instance, that is defined by the minus the indicator of the y being 1 times log of eta theta x minus the indicator of y being 0 times log 1 minus eta x, 1 minus eta theta x. So what this means by that is if your data point has label 1, then your loss is going to be minus log of eta theta x. And if y is 0, then you are going to incur the loss minus log of 1 minus eta x, right? And the fact, so if you are given samples, you're going to add the sum of the empirical losses given samples, and then you're going to minimize this. So that is the typical way. And the fact is that when you take the expectation of this binary cross entropy loss with respect to the underlying distribution defined as above, then it's minimized if and only if the probabilistic classifier actually becomes the underlying conditional distribution of the label being 1, right? So this, I believe that this is very familiar. I mean, you're very familiar with this kind of stuff, and this is just a reminder. Okay. Any question so far? Okay. Then we can interpret the binary, the noise contrastive estimation based on this framework. So I'm gonna plug in the data generating distribution for the class 1 and noise distribution for class 0. Right? And if you recall the NC objective function, then this is the expression. And if you define eta theta x by this, which is, by the way, between 0 and 1. And here phi tilde, you can notice that phi tilde is the unnormal, it doesn't need to be normalized one. It's an unnormalized. Still in the extended family, it's an unnormalized one. Then we can rewrite this by expected value of log eta theta plus expected value of log 1 minus eta theta with different distributions. And you can notice the similarity between the binary cross entropy loss and this. So yeah, so we can write this as -2 times expected value of the binary cross entropy loss, which means that maximizing this with respect to theta is equivalent to minimizing BCE. So maximum of this so NC objective is attained if and only if the eta theta x becomes equivalent to the underlying conditional probability. And we noted that it's this by Bayes' rule, and we parameterize by eta theta by this form. And this can happen if and only if phi tilde is equivalent to PT, the data generating distribution, which is P tilde theta star. Phi tilde theta star, sorry. So, and this is if and only if this happens if and only if when zeta is actually the zeta star. So this proves the previous theorem where the maximizer of the NC objective recovers the desired parameter theta star. Okay. Yeah, please let me know if you have any question at this point.
Yeah, I guess one little thing to mention is like in the theorem, it mentions that the support of your data distribution should be, no larger than the support of your noise distribution.
Right.
And that is because in your ratio computation, if that condition is violated, then you will get divided by 0.
Right. Yes. Yeah. Exactly. Yeah. So that is one technical condition for this parameterization to be, parameterization to be valid. Yeah. Thanks for pointing that out. Right. So this is the standard interpretation of binary cross entropy. The noise contrastive estimation principle. So to recap, so we formulated the parameter estimation problem into the optimization problem, and it happens to be interpreted as the binary classification problem with some hypothetic labels attached to the data generating distribution and noise distribution, right? So this is a quite interesting principle. And let me give you some facts on the statistical properties of NC. So given samples, I told you that the estimator is taken as the maximizer of the J hat NC. So this is what we are looking for in the, so we aim to compute in practice given samples. And there are some performance guarantees, theoretical performance guarantees in terms of asymptotic consistency and asymptotic normality. In parallel to that, those of the maximum likelihood estimators. So what I meant by that is under some regularity conditions on the noise distribution and data generating distribution, we can show that this theta hat and C converges to the desired parameter in probability. So that is that is a consistency, asymptotic consistency we can establish. And under the same condition, what we can further show is that the scale version of this error between the estimator and the desired parameter follows the asymptotically the Gaussian distribution with some covariance matrix sigma as a function of the noise distribution and the data generating distribution. And in particular, based on this asymptotic normality, what you can see is that in the asymptotics, the MSE of this estimator is going to be roughly the trace of this covariance matrix divided by n. Right. So this is this is a typical argument and typical result in the parameter estimation literature. Right. So one remaining question is, one key and possibly research question in this area of noise contrastive estimation principle is how to choose noise distribution, or what is a good distribution for PN. So I told you that there are two requirements basically. So it should be easy to sample from it to approximate this expectation, and it should be easy to compute the density to evaluate the objective function. And based on the previous slide, we can also kind of expect that it leads to small MSE in the sense that the trace of the sigma, and I told you that sigma is a function of the noise distribution and the data distribution. And we hope that the noise distribution is giving a nice shape of this covariance matrix so that this becomes smaller, up to constant for sure. Yeah. Okay. So there are simple choices like Gaussian uniform, Gaussian mixture, and so on. But oftentimes these are not very satisfactory because intuitively we want the noise distribution to be close to the underlying data generating distribution. And why? And here is an hand-wavy argument. So the hand-wavy intuition is that if the noise distribution and the data generating distributions are far apart, then the classification, the hypothetical classification problem becomes too easy, right? In the sense that, in other words, it might be possible that the objective achieved by the NC estimator might be, so it could be that this is close to the objective value at the desired parameter, while the estimated parameter is still far from the optimal. So this can be happening like if the landscape of this J hat NCE gives you like this flat surface around theta star. So this might be very close, but this might be very far.